then for the past 5 years, they're a UK manufacturer, manufacturing variable speed drives in the UK, which is quite unique in itself. Prior to that, I worked for a company called Parker, who are very much a very large American engineering company. And prior to that, I worked for a company called Eurotherm Drives, again, another British company, also making variable speed drives. So I've actually been in the industry now for just short of 34 years. So that's a bit scary in itself, looking at these very young faces. So, and again, engineering, I think, has changed an awful lot in those 34 years since I started doing this. But right at the very, very beginning, the only control that you had of a motor was to control it using a DC drive, and it had to be a DC motor with brushes. So that technology has changed beyond recognition over the past 20 years, really. So obviously that's my speciality, and I understand what you guys are doing as a project where you are looking at trying to re-engineer something and try and make it better. So what I wanted to do was just introduce motors generally, and just as you're looking at your applications, just to see if there's anything that you can see that you go, oh yeah, I think I understand roughly what that's doing, and maybe give you an idea of maybe how you could change a motor or just change a technology sometimes to improve it. Okay, so firstly, what I did last year, I actually put together this. It's not a particularly professional video, this. So what I wanted to do is just show you our factory. We're down on the south coast, down in a place called Arundel, which is near the Southampton, and this is where we do our manufacture. It's only 6 minutes long, but I thought this was better than death by PowerPoint for an hour. So let me just run this. It's probably got some very cheesy music to it, which I may turn down. But I just want to sort of show you this building. Like I say, this building has been manufacturing our variable speed drives for since 1987. And what it basically does here is take us into the factory and round production and just give you an idea of what we're doing at the moment and the sort of stuff that is involved in just a manufacturing process for making equipment. So it just gives you an idea. So the plant, the factory itself, as I said, we're going in the front door here. You can see we have a full reception area in the front door. We're going to have a look at production. As I said, not particularly professional, okay, as you can see. The other thing that also happened is I actually did this video over lunchtime. So as we go around the factory, there's very few people in the factory. It looks very empty as well. So I should have possibly redid this again. But as we come in here, we have a demo room right at the very start of the building where we can actually show customers the product and we can demonstrate the product in action. But in effect, inside this building, not only do we manufacture the product, but we also do complete design of the whole drive product. So upstairs, this is actually the sales office upstairs, and on the opposite side we'll go through into the technical department in a few minutes' time. But as I said, what we do here is we do the full design process. So right from scratch, we do all the mechanical design, we do all the electrical design, all the software design. That's all done in-house by ourselves, which is actually quite unique in the drives industry. The drives industry generally is dominated by predominantly by Eastern European product and Chinese product as well. So there's a lot of competition in the field, low cost competition. So to be able to manufacture it in the UK is quite unique, to be honest. So we would compete with companies like Siemens and ABB, who you may have heard of, some of the companies like this. So here we have where are we now? Yeah, so that's the R&D department. At the moment, we're in the R&D department. We've got quite an active R&D department. We are looking at continuous product development, and we are in the process of launching a brand new product at the back end of this year. But in effect, what we do here is we actually manufacture both for stock and also for customer orders. So you can see there's an awful lot of half-built near built stock in what we call the vanilla condition here, and that's then finally assembled, usually in a one-off sort of build cell. It's not a continuous process line, we actually build in cells rather than process. And we also, as we actually, we fill the line with new stock, we have deliveries every day coming in and filling the shelves with the components ready to build the products. So it's like a Kanban system, so these are filled, so the operators and the guys on the manufacturing line actually have those delivered to the cell for them to manufacture the product. Products are then fully tested, so once they've been through the production line there, that's just looking down the line there, the products are then automated, everything is fully tested, there's full test rigs, and these are all drives waiting here just to be ready to be tested. These are pin boards here, which actually, the drives are actually put on a pin board and run with a motor, so everything is 100% tested before it goes out the door. Typical test rig that we would use to test the product. I scanned down the side here because that's actually probably the oldest bit of equipment in the building, so that's a dot matrix printer if you've never seen one before. So basically that just shows you the test condition. So as we run through the test conditions, we're running through a number of test conditions, and they have to all go green for you to move on to the next stage. If something goes red, then that's inspected and then reworked. The idea being that once the thing's actually fully tested, if it does need to be reworked, this is the department just at the back of the factory where we can do rework. Hopefully we don't keep them too busy with what we do. And obviously, with having, each drive has around about 4,500 components, so we have to do a lot of stock management to make sure that all those components are available continuously for us to actually manufacture the product. So once it's actually completed, it will either be completed for a customer order. If it's for a customer order, it'll be completely boxed up. If it's built for stock, it's stocked on these shelves. We have over 500 drives already on the shelf, ready to meet any sort of quick demand customer orders. Again, another thing that you don't maybe consider when you're doing manufacture is we actually have had packaging completely designed to hold the product. So wherever you ship it around the world, the product can be shipped, it doesn't get damaged, and the actual packaging design is sometimes as important as the drive design, because obviously if you're shipping it around the world, you want it to arrive in one piece. So we have bespoke packaging. And also there's a bit, we film stuff with foam. And again, then that's ready for dispatch. And at the moment we have couriers arriving 4 times a day to actually pick the product up. And that then is then shipped around the world. From our manufacture, about 80% of our product is shipped outside the UK, and out of that 80%, around about 60% is shipped outside the EU as well. So we are very much an international company. So that was just a very quick introduction to the factory. Let's jump back to what we were going to talk about in a bit more detail. So as I said, my expertise is in motor control. So we're just going to have a little look. Most things that rotate, especially, have got some sort of motor control inside them. Some of it's fixed speed, but also there's very, very many of these that are variable speed control as well. And to vary the speed of a motor can be quite a challenge in some cases. Now there are lots and lots of different motors. So to give you an idea, I just sat down and put a list together as many as I could just think of. But all these are completely different motors, so slip ring motors, axial air gap motors, permanent magnet motors, wound rotors, all those. So there's an awful lot of different motors that you can see. And you can see them in all sorts of different applications. But what we're going to concentrate on, we're going to concentrate on DC motors, AC motors, and then also servo motors, just as a general thing. Because I think if you've got an idea of how they work and what you're looking at when you're taking stuff apart, it gives you a bit of a clearer indication of one, how it works, but secondly, possibly how you can improve it. So this is what it all sort of comes down to. If you actually take a magnet and you produce a current which is at 90 degrees to the magnet, you produce a force. Okay? And as long as that magnet and current is at 90 degrees, then you're producing the maximum force that you can possibly create. The simplest way of remembering this is Fleming's left-hand rule. Okay, so if everything's at 90 degrees, you've got a current source, you've got a magnetic field, and it produces a force. And just about everything that you're doing in motor control is trying to keep the magnetic field and the current source at 90 degrees. And if you can do that, then you're generating full torque. What we do in the motor world, obviously that's a static example, just showing a singular force. What we actually do is we turn that force into a rotational force. And we do that literally by having lots of different poles or magnetics, and when they're opposite, then they actually do rotate. But all the time, as you're rotating, as this is rotating, does this rotate? Just give me a second, it might do. Oh, here we go, fantastic. Was that it? Okay, but as you saw, as it rotates round here, when the force is at 90 degrees, it's creating full torque. As soon as it starts rotating, it's outside that 90 degrees. So then you do another winding, which brings it back to 90 degrees. And that's in effect the construction of a motor. So if you look at a DC motor, which I said originally that's every motor that you were trying to do variable speed, the only real way of controlling that was to control a DC motor. And the reason that you can control a DC motor, this is a sort of typical DC motor. So it has a field around the outside, it has an armature in the middle, and mechanically at the back here it has what we call a commutator, and that commutator has lots of different segments on it, and then there's a brush that fits on that commutator, and as it rotates, it picks up each section, and that keeps that thing at 90 degrees as the thing is rotating. So mechanically, in a DC motor, because this is all done mechanically, there is always a 90-degree angle between the current and the magnetic field. And that's why it was so easy to control the DC motor. So just typically, if we have a look at it, just as a drawing, there you can see the commutator. So as the motor rotates, it actually takes a different segment of the commutator, which does a different winding in the field, and as it rotates, it actually just keeps everything at 90 degrees. So why would you do that? As I said, as soon as you move these apart so that you're actually not doing 90 degrees, then the torque in the motor reduces. And what you're trying to do always is you're trying to get as much torque out of the motor as you possibly can. So in the DC world, this was, like I say, very easy to do because it was mechanically linked to this. And because of that, on a DC motor, the current of the motor is directly related to the torque of the motor. Absolutely, because it's mechanically connected. Okay. And you will see this right the way through to massive motors that are controlling mines that might be thousands of kilowatt, right the way down to little small DC motors that even some of the earlier phones used to use a little DC motor as the vibrating motor inside your phone, and they were absolutely minute. But again, exactly the same construction as this. But really, what you want to try and do, and the more common motor, is an AC motor. Okay, so the AC motor has a completely different construction. So the AC motor still has a winding on the outside, which is there, but also in the middle of it, it has the winding in the middle isn't mechanically connected to the outside world. So the outside winding induces the voltage into the motor. to be able to rotate the motor. Now, because of that, well, let's firstly look at the torque characteristic of an AC motor as well. So if you actually look at the torque characteristic of an AC motor, and this line is slightly incorrect. The number one angle here should be slightly lower here. So at 0 speed, or what we're looking at here is a motor would run, basically to run the motor, you need to put an AC frequency into the motor. So normally, if you're looking at a standard single phase or 3-phase supply in this country, that would run at 50 hertz. So you're looking at 50 cycles a second. Outside here, it could be anything up to 60, 65 hertz. But at 50 hertz, which is full speed, if you were to actually run the motor right away at full speed, at full frequency, then as you can see, the torque actually drops off considerably. And this is all to do with the slip of the motor. Because you've got a stator and a rotor, the rotor is always lagging behind. All right, and because it's lagging behind, you're always trying to correct this 90-degree connection into the motor. And again, at 0 speed, when you start to run at 0 speed, the actual efficiency of the motor, the torque efficiency of the motor, is a lot poorer than at this sort of nominal speed here, which is the point where you're looking at 3, okay, on this diagram. So to give you an idea, if you were to actually look at the mechanics of the motor, if you were to run a motor, an AC motor, with 4 poles of windings, its theoretical speed is 1500 RPM. But 1500 RPM will put you right away at this part of the curve here, which means actually at 1500 RPM you don't get any torque in the motor at all. So what you find, if you look at any of these motors and look at the nameplate, even though it would be nominally 1500, you'd expect to see that to say something like 1440 or 1470 RPM. And that's because that 1440, 1470 is where that number 3 is. So it's giving you the best torque capability of the motor. And the difference between the speed at number 3 and the speed pretty much at number 4, that's in effect how efficient the motor is. So the closer they are, so the closer that number 3 is to the full theoretical speed of the motor, means there's less slip in the motor, so therefore it's more efficient. So straight away, if you look at the motor, and there's a big difference between its nameplate speed and its actual theoretical speed, you can see that that's quite an inefficient motor. So straight away I can go, right, okay, well if I put a more efficient motor in there, then actually it's going to take less current to drive it, to give you the power, so you're actually saving energy in running the motor. So again, it's just something to look at when you're looking at the motor. They tend to be, the nameplate on these types of motors tends to start at sort of round about sort of 0.25 kilowatt, okay, possibly right the way through the full range. So if you were looking at something like a lawnmower motor, for example, then you'd see on the nameplate of the lawnmower motor, you'd see that RPM, and you'd be able to work out what that difference is, and you'd be able to, it's a good indication, you know, it's a really quick result, is to put a more efficient motor on. And in fact, what the industry is sort of trying to do generally from a motor design is try and make these motors as efficient as they possibly can. And there's been a lot of work done on motor design to try and move that number 3 further and further close to the theoretical speed of the motor. Okay. And there's quite a lot of European regulation, or European standards, which allow you to work out whether a motor is high efficiency as well. And that's in effect what you've been looking at in real terms. Now, the other sort of motor that you also might get involved with is a servo motor. Okay. So the servo motor looks very much like an AC motor. Okay, so whereas the AC motor has got a rotor and a stator, this rotor, as I said, is induced by the stator, so it actually gets its current from the stator. In a servo motor, the centre of the servo motor is a magnet, so it's permanently there. You've permanently got magnetism in that motor. So in effect, by controlling the armature of that motor, you actually control the rotation. The other thing is that, again, on an AC motor, when you've got a stator, because it's induced, it generates heat. So actually you do have to be very careful on cooling a standard AC motor, and usually if it needs a lot of cooling or it's running slow, it'll have forced ventilation on the back of it to cool it. With a servo motor, because this literally is a magnet and it's not generating any heat in the core of the motor, you tend to find that these motors can run right the way through the speed range without any additional cooling. So again, it's something worth looking at. The other thing is that the servo motor tends to be used, all the motors that we talked about so far before the servo motor have been like speed control. So you're looking at the speed of the motor, varying the speed of the motor and having accuracy of speed. In a servo motor, these are also used, and the command can be step and position rather than speed. Okay, so in effect what you're doing is you're moving from A to B, and you're moving accurately from A to B. So for example, if you looked at a printer, for example, where you maybe want to print across a certain path, or if you were looking at even 3D printing is a classic example. If you've seen a 3D printer, those are servo motors on there, and the command that's going in there is literally step and position. So it's saying I'm going to do so many steps in a certain time, and that time can be shortened, and that's in effect what you're looking at doing the control. A DC motor needs some sort of control. An AC motor can run fixed speed with no controller. A servo motor always needs a controller. Okay, so again, if you've got a servo motor in there, you can see that you can see it straight away because there will be some sort of controller in there. Now, as I mentioned with the DC motors, some of those DC motors, if we have a look at the mechanics of that servo motor, so basically what you've got is this magnet in the middle, and then to try and get the most torque out of the motor, rather than just having a circular set of magnets, what these have is they have magnetic cores. So this is giving you as much magnetic force in the motor as you possibly can. So obviously the higher that force, the more torque you can get out of the motor. So again, inside the motors there's an awful lot of this construction going on. They're quite complicated inside. As you can see, this would be what you'd be looking at from the motor. Okay, I think that's worth a bit of that. So if we're looking at cooling, as I said, on some of the DC motors, you would be looking at different types of cooling. There's a full IP range of protection on a motor, which includes IP is the ingress protection from the outside world. The IC rating is the cooling method used to cool the motor. So again, this tends to be on a nameplate, so you can see straight away you've got an IP rating. The cooling itself, as you can see, some of this cooling is just if you ignore the first one, that's pipe ventilated, but if you come back to IC 141, you'll see that's a fan on the back of the motor blowing over the motor. Hopefully you can make out the picture. That's the sort of standard AC motor cooling method. So you have a fan on the back of the motor, so as the motor reduces in speed, the fan slows down as well. So again, you actually reduce the amount of mechanical cooling. So what you tend to find if a motor is running over a big speed range, like I say, it has an additional fan on it. Again, if you want to try and make it more efficient, it's a way of maybe looking at removing that fan. So if you've got a big motor and it's got some of these motors, if you're looking at 100 kilowatt motors, for example, it might have a 4 kilowatt fan on it, and that's going to be running permanently. So straight away, without running anything, you're using 4 kilowatts worth of power. So you can find some way of removing that, possibly even going down the route of a servo motor, although the motor would be more expensive. Then you remove 4 kilowatts worth of the power straight away. So if you're looking at it, again, have a look, see if the impeller on the back of the motor is connected to the rotor, or whether it's actually a force vent, and it's another way of just making it a bit more efficient. So if we look at these in a bit more detail, just looking physically what they look at when you start to look at slightly more industrial motors, but you'd probably see an AC motor similar to this inside anything that was above sort of 2.5, 3 kilowatt, that sort of size. And again, a DC motor with a big forced ventilation fan on the back of it, and then also the servo motor, which again doesn't really need any cooling. But physically you'll find that AC motor is usually the bigger of the three because it has not a lot of cooling, The DC motor tends to be smaller, especially when you look at bigger sizes, because it's force ventilated, and then the servo motor is smaller again. What you tend to find with servo motors also, because on all these, because you're looking at speed control, on a servo motor, the inertia of the motor is as important as the torque output. So what you want to do is the speed, the acceleration speed of the motor, you want to, if you've got to go from 0 to full speed in half a second, quarter of a second, then the inertia of the motor is important. So what you tend to find is a lot of the servo motors are long and thin. So again, it's something worth checking, because again, when you look at the motor, you can see that it's sort of long and thin. So how do you control them? Well, the control itself, we are going to look inside the black box, but there's usually some sort of black box control in there to control the motor. And in effect, that input into the black box can be 230 volt single phase, it can be 400 volt three phase, it can be DC, 12, 24, 48 volts. Those sort of typical voltages that you see coming into the black box. And the technology inside the box isn't a great deal different, but you define the drive by what its output is. So as you can see here, you've got variable AC output, you have a DC output, and you can see what you've got there. So that actually means, and also from that you also have the control. So whether you want to run it in speed control, in constant torque, okay, so you've got the full torque capability of the motor, in quadratic mode, fan law, so you do energy saving, and then also speed, as I said, speed and position, as we talked about with the servo drive. So just to give you an example, if we look at all those will give you an AC motor or an AC drive or a DC drive. This is typically what you'd see from an AC drive or a DC drive or a servo drive, as we saw for set and position. So if you look inside the DC drive, the actual control itself, the DC drive is the most simplest thing to control as well. So again, this is another thing to look at. If you just see thyristors inside the drive, in effect, all you're doing is changing the voltage on a DC motor, because it's all mechanically connected together. So all you do is you've got a device in there, and if you turn the device on completely every single time and it pulses right the way through, you've got full voltage out there. If your electronics is only turning it on half of the time, you only run at half speed, and then obviously if you only turn it on a little bit, then actually the speed reduces, and that can go right the way down to 0 in that form. But because it's a switching device, what you find is away from full speed, because it's switching and it spends a lot of time off, it actually generates quite a bit of noise, as well, electrical noise. So again, that's another thing that you also have to have a look at with variable speed drives generally, and there can be additional components in there that show you what that's all about. Slightly different with AC. Obviously with an AC three-phase supply, you've got three phases that you're looking at going into the motor. We looked at this curve earlier on, and this is the motor curve, and as we saw, the 0.3 is the best torque capability that the motor can generate. So what you want to try and do through the full speed range is keep in that part of the curve which is at number 3. And you do that by keeping the voltage and the frequency ratio the same. So full speed on a 400 volt motor, it would have 400 volts in there and have 50 hertz. If you run it at half speed, you'd see 200 volts and you'd only see 25 hertz. So that keeps that ratio the same. So therefore, as you decrease the speed, it actually moves this curve further and further back, and that's what they call constant torque. And that's why most AC controls are quite complicated in the path, because what they're doing is they're keeping this constant torque ratio inside the drive to be able to do this. Now the other neat thing about this is what you can then also do is what they call variable torque. So if you have something like a fan or a pump, and actually as the speed increases, the torque requirement increases. If you have that, then actually you can run the thing in quadratic mode or torque control, and what you end up doing is making something that's a lot more efficient. So the beauty of running in quadratic mode is if you can halve the speed of the motor, you actually only use a quarter of the power. So if you've got an application where the motor is just running fixed speed, or it's got a very, very basic constant torque control on it. Again, you can improve it by making it quadratic control and reducing the power requirement quite considerably. So again, it's something just worth having a look at, just to see if you can improve and whether it actually follows that constant torque rule. To the point that if you run in quadratic mode, you only need to reduce the speed by 10% to get a 30% saving in the motor. So it's quite a big saving to be had to be able to do that. But like I say, most other industrial applications would run using constant torque. So here's your constant torque curve. So it keeps torque right the way down to zero speed. So you've got full torque. So the power it increases as you run up in speed, but actually you've got this capability. Also, because you're changing both the voltage and the frequency, at full voltage and 50 hertz, it's running at full speed. So you've got a choice. You can now increase the frequency, and the motor will also increase in speed. So you've got that capability also of increasing the speed of the motor by increasing the final output frequency from the drive. And if you were to run that at 100 hertz, it'd be running at twice the speed. Okay? And again, sometimes on an application, if you can run the thing faster, you actually mechanically you can reduce the physical size of what you've got inside the product. What we're tending to see now in the automotive industry with electric cars, the original electric cars, the motors that were inside those electric cars originally were running at around about sort of 15,000 RPM, which is still quite fast, but it's nowhere near the speed of a petrol or a diesel-driven engine. So now what's been happening in the automotive industry is that those electric motors are now starting to increase more and more in speed. And as they get more speed out of them, they actually physically decrease in size. So again, you get a smaller motor because you're running it faster and generating torque at a faster speed. So some of those motors now are running possibly 30,000 RPM, that sort of speed. It's incredible what they've been able to do in some of those motors. Okay, so that's my quick download on motors generally. Does anybody have any questions? I do have, what I'm going to do now is I've just got a few slides just to show you, just from a component point of view, just doing a little bit of component recognition. So when you're looking at your applications, if there's certain components you can pick out, you can just see what they're doing in circuit. So just again, just if you are looking at a PCB on anything that you're taking apart, you can go, okay, that I can spot those components, I can see what they're doing here. Does anybody have any questions on that at the moment? Okay, I'll carry on, not a problem. So what we're just going to have a quick look at, obviously on a control board, to control any of these motors, or anything to be honest, electronically that you're looking at, it's pretty much built up of these main components. So you're going to be looking at resistors, transistors, capacitors, diodes, microchips generally, and then also some sort of transformer. And again, it's amazing when you take stuff apart, when you actually see, you can spot these quite quickly when you just know roughly what they're going to be looking like. So that's a sort of typical PCB that you'd maybe look at of a control. And if you have a look there, just at the very top corner there, you can see the transformer. So, and that is literally a wire coil, a wound wire coil at the top of the transformer. These are resistors here, but we'll have a look at a little bit more detail in resistors. Well, we'll look at all these components a little bit in more detail in a second. So, capacitors, again, very much dominant on a lot of AC equipment is a capacitor, and then also microchips, which are doing a lot of the electronics, which you can actually do in using raw components, but the microchip takes a lot of that away. And then also transistors, which you can look at on the board as well. So let's just, again, let's have a look at them in a little bit more detail. So resistors, this is a sort of typical old, what I'm going to call an old-fashioned resistor. Okay, so this is colour-coded, so you can work out what the resistance is in ohms on there. You can work that out. And if you're looking at a very old bit of equipment, then you may see resistors like this. These are through-mounted, soldered into a board. And again, if you're making the thing more efficient or you want to reduce the physical size of it, if you see this sort of resistor in your whatever you're looking at, you can go, well, actually we can make a more modern board here. We can actually improve the build of the board and move away from old-fashioned resistors to what's more like a more modern resistor. And that, you see, you can say R36 on the drawing. It's R because it's a resistor, but you can see that's a surface mount version of one of these. Massively reduced in size. Surface mount on the board, it means you can very, very quickly reduce the board itself. And resistors are used to control voltage. They're used in circuitry to basically control. Well, like I say, if you're looking at amplifier circuits, it's something that you would have a look at, and you'd see quite a lot of resistors doing that. So another device that you'll see a lot of is transistors. These are transistors which could also be called thyristors. We talked about these with DC, as we said. So, and what this is a device that switches high current using low current. So, in effect, you have a leg which switches it on and off, and it basically just passes high current through the rest of the circuit. So, the typical way of seeing a resistor is it's got 3 legs on it, but they can be completely different in their form, what they look like. So, they can be little resistors, little transistors like this. They can be 3-legged. These tend to be slightly higher power, so they've got a heat sink on them. And when they go even higher power, they need quite a substantial heat sink on, which is what that metal casing is. And those are all exactly the same functionality. And again, it's just switching larger current, using small current to switch larger current in a circuit. Diodes stop the flow of voltage in one direction, so they only allow one direction of flow. So if you're building a circuit and you don't want voltage to go back through the circuit, then you will see a diode in there. But again, very, very, very different forms of these diodes. This is a typical diode that you'd see really, really easy to recognise. But diodes also can be quite ceramic like this, and also then start to look like resistors. So you can see, you just got to be a wee bit careful on what you're looking at. What you tend to find is that they have either a grey or a black end to them, to show them that they're only going in one direction. And then the most common diode that you'll probably see every single day is the light emitting diode, so an LED. Okay, and that is a diode exactly the same as these and these. It just actually has an element in there that lights up. Okay, and again, as you see, as I mentioned, this allows voltage in one direction. All right. So again, when you're looking at a diode can only be run in one direction. If you put an LED in the wrong way around, it won't light up, because it actually needs to go through the circuit in the right direction. So again, something worth looking at. Okay. Capacitors tend to be used to store voltage. Okay. So again, if you're smoothing a circuit, you put a capacitor in there, and as you can see, there's lots and lots of different shapes of capacitors. But they tend to be this sort of chunky sort of block type thing. But when you start to look at smaller capacitors, then that block is just literally in a blob, looking like that. And when they go really big, then they start to look like this. You'd see typically, if you're looking at a single phase AC motor, so one running off 230 volts, and it's a single phase motor, one of the easiest ways to spot if it's a single phase motor is it has a capacitor like this on the side of it. And the reason being is that because it's only single phase, the motor needs something to start it to turn. Once it's turning, it'll keep turning and then you can control it. But in single phase form, you need something to start it. And so the voltage is stored in the capacitor, and then that allows you to start the motor. That's a real easy one to look at, especially on some of the applications. You go, what's that by the side of the motor? It'll be a capacitor, and it just allows you to start it. Straight away, you know that you've got a single phase AC motor on your application. So that's a really easy one to spot. And again, they can be this block form as well, which tends to be the sort of more modern capacitors in a circuit as well. And then obviously microchips. So a typical microchip in the early days, the very early ones, and you see them all the time as a chip called the 555 chip, which is in effect a timer. But you can have amplifier circuits, all those, all done in chip technology. So some of these microchips, if you were to actually try and do that in hard component form, can be 12, 15 times the size in component form, but you can just put a chip in there. So again, if you're looking at a circuit and you're looking at something that's, and again, the low cost circuits tend to use just components. But you might be able to look at that component and go, actually this is an amplifier circuit, which I can do in a microchip, and I can physically reduce the size of the PCB, I can make it a little bit more easy to manufacture, those sort of things. And like I say, there's, if you looked at microchips and you looked at the numbers, every microchip, there are literally thousands of different microchips all doing different functionality, and they all have a number. So again, if you actually look at your circuit, normally the number's on the top of the microchip, you can look it up and it'll give you the circuit that's inside that microchip. And some of them are very, very advanced. So that just gives you an idea. I just wanted to just show you, if you were looking again at the control and you're looking inside your items that you're looking at, and you wanted to just recognise some of these very familiar products, it's worth being able to see and just work out how they all work. Yeah. Okay. That's me done.